guys, welcome to my YouTube video, and today I will be displaying how the sensor here, servo here, switch, and the LED works. As you can see, it lights up, and when the switch is turned on, utilizes off, on. There we go. So we used assembly coding language. Now let's try to inject, exit, and then re-inject this. Set this to the proper COM, and again, so then run. You can see uploading, and we're done uploading. So this is the code that we're using. We have the .s file and then .ino file. There we go. So this is how to turn on the servo. Right here. On, off, and then let's try this. Wait, sorry. Here we go. So there, our sensor is clearly working with our LED. We're going to control our LED, as you can see there, and our servo is controllable as well. Now this is a 180-degree servo, so it works like that, and this is our code. Now I will explain the code. Hello guys, so this project is basically an extension of my finals project, which in the other case is supposedly a robot arm, but I had to opt for a disc display. So before going to my finals project, which is in another video, let's talk about this first. So what's the purpose of .s and .ino? So what we're doing is essentially calling the functions in .s. We're calling it as a global in section.text is because we're initializing it as callable functions outside of the .ino file. So here we have init system and servo control. Init system is basically us initializing everything. Like for example here, what we're doing here is essentially initializing our parts, and in the other half we're setting our timer. This is the setup for our timer. We're setting it at 0x07. We're storing it here, and what we're basically doing is we're loading the values of 0x96 to R16. So why are we using R16? Well, that's because these R16 to R31 are designated general purpose registers for the sake of ORI or R0 commands, meaning that these ORI commands and in commands may have a difficult time working if we're not using the general registers for R16 to R31. But there are also general registers that function well with LDI but not ORI, and these are the registers from R1 to R15. That's why we're also using these, so that we can have a simplified code and it works well without running into errors. So now let's take a look at how this will be used. So after initializing everything, including our timer and our PWM, not the PWM, I'm sorry, the timer and the ICR1, this is our RCR. This is the initialization for our ICR1. This is for the OCR, high and low, both. And these are for our pins. Basically, what we're trying to do is load them into specific values that hold the houses of these pin mapping or map pins. And ORI is basically comparing R16 with this value, meaning that we are creating an 8-bit and comparing both. And whatever the value that remains is stored into R16, and R16 is stored into 0x0a. That's just an example. So that's how it works. Now let's proceed to the logic, the sensor servo control. So this will be called within our .ino file as a loop. So constantly our ATP Mega 3, I forgot the value, basically our Arduino Nano will constantly call this, and we have our other functions right over here, and these functions are meant to support the main logic presented by servo control. So what we are doing is we're assessing if R18 is, we're embedding 0x09 into R18, and we're comparing it, if whether or not it's high or low. Now, what happens next is that we bounce directly to IR low, which is here, and again we are comparing, and what happens is that we are checking if IR is low, then display this, meaning that the LED won't light up. And if it's high, right over here, we allow the LED, or we allow the system or the microprocessor to give us control of the servo, in which we go to the process and the switch. This is basically us lighting up the LED, and if it's low, then we won't do anything. So here we go, process and switch. After knowing that it's high, IR is high, that means that we are able to use the switch already and move the servo. Right here, we are checking if switch is low. We are comparing both value of 4 to R18, and then we're checking if switch is low. We jump directly to what happens, which is us changing the pulse width modulation of our servo so that it moves to 90 degrees, and if not, then we go back to moving it to 180 degrees. And if it does move, sorry, not 180, 45, the movement is just minimum. And if it does move to 45, then that means we execute an SVC, which is the return value, meaning that we will just return and redo the cycle over and over again. So what makes this unique? What we're basically doing is we're loading data into R16, we're storing it into 0x09, which is what helps us modulate the pulse width, what helps us execute the pulse width modulation. And after that, we're just using AND I and out, AND I to compare 0x7F to R16. Now the 8-bit value here will be compared directly to the 8-bit value here, and whatever residue is left will be stored into 0x08. So this is how my code works, and basically the flow is that we start off by checking if IR is low or high, and then jump to our jump to process switch if ever it's high. If it's low, we execute the same thing. That's why earlier there are times where you could not actually move the servo without clicking. And that's basically my code. That's an in-depth explanation of this, and I hope you watch this video before watching the finals, because this helps explain a lot of the things I wasn't able to explain on my finals video, because these are just the basics of how it works.